All right, so we're going to take a look at number 6, 7, 8, and 9 on the team round from 2014. And this includes one of my favorite math counts problems of all time, number 10. The mass fulcrum geometry stuff. We love it. All right, so let's start with number 6. A, B, and C, I'm just going to go by their initials, play a game in which they take turns adding 1, 2, 3, or 4 to the sum in order to create a sequence of prime numbers. That's got to be prime, and you have to add 1, 2, 3, or 4 to it. Abby must start with either 2 or 3. If she chooses 2, then the next player, in this case B, can add 1, which would make 3, or you could add 3 to make 5. You just have to have a sum that is a prime. So it goes on to say, and it gives some more examples so that you understand the game. So then the question, here's a question. So A, B, C take turns in that order until there are no more primes that can be made by adding 1, 2, 3, or 4. And the game ends. The player who makes the last prime wins. If Bartholomew wins, how many primes were made? Well, this makes things a little bit tricky because Abby can start with 2 or 3. And we don't know which one she's going to start with. So we're going to make the assumption that she's going to start with 2. So if A starts with 2, we have a sum of 2. And so this is going to be the number used, and this is going to be the sum. Which means that B, well, he can go one of 2 ways. He can go with a 1, or he can go with 2 or 3 rather. But let's just pretend he goes with the 1. So that gives us a sum of 3. So at this point, C can go a couple ways. They can go with a 2 to get to 5. You can go 4 to get 7. But we're kind of guessing and checking in this case, so it doesn't matter. I'm going to try things until Bartholomew wins. So let's go with 2. So if I add 2 to 3, I get 5. So now we're back to A. And so they can go, well, they can only get to 7, right? Because all the other numbers that are within 4 of 5 are going to be composite numbers. So we're going to go with 2. So that's a 7. Now B's back up. And so the only one we can get to now is 11. So we got to go with 4 to get to 11. So C is stuck with adding 2 to get 13. We're back to A. So 13, well, 17. We go 17 or 19. We can go 19 but we can go 17. So we can add 4 to get 17. Well, 19 is our next prime. And 20, 21, those aren't prime. 18, definitely not prime. So we can only add 2 to get 19. So we're up. C is up. And so if C is up, then we can get to 23 by adding 4. And 23. So 24, 25, 26, and 27 are all composite numbers. So that's not going to work because our B guy didn't win. So let's try another way of doing it. So let's say again, A starts with 2, and let's say instead of adding 1, B adds 3, because that gets me to a sum of 5. So then C has got to go 2 to get to 7. It's A's turn again, and again we gotta go to 11, right? So we add 4 to get 11. On B's turn, we have to add 2 to get 13, because there's not much more we can do. Then we've got to have C add 2 again to get 17. That leaves A, the only choice for A is to add 2 to get 19, which means B is up again, and we can add 4 to get 23, and we're done. And B won. So we know this is the order that the game happened in. And we don't really care if A started with 3, because the problem does not say which game has the least number of plays or the most number of plays. So we know even if A started with 3 and B won again, we know it has to at least equal the same number of primes that were used in this sequence. So we have 1, 2, 3, 4, 5, 6, 7, we have 8 primes. So that means the answer for 6 is 8. For problem 7. All right. This one is actually not too bad, folks. How many positive integers less than 1,000 do not have a 7 as any digit? Well, it has to be less than 1,000. So we have 3 different circumstances. We have 3-digit numbers, we have 2-digit numbers, and we have 1-digit numbers. Well, in our 3-digit number, how many different numbers can go here that are not 7? Well, we have 1, 2, 3, 4, 5, 6, not 7, 8, 9. And we can't put a 0 there either. So that means we have 8 different possibilities. But we have 9 possibilities for these other 2 spots because we can put a 0. So 8 times 9, so 9 times 9 is 81. 81 times 9 is, I don't feel like I did that right, but whatever. All right, so if I add, I totally did not do that right. Oh, I'm allowed to use a calculator. Let's use a calculator. All right, so if I use a calculator, so this is the problem with doing math at the end of the day, and you're trying to do it quickly, you tend to make errors. Okay, you get 6 for it. What? How did I put that wrong? Oh, because 8, this should have been an 8, that's why I wrote the problem wrong. That is the story of my mathematical life in high school. All right, so we have 648 different numbers that have no 7s, but 3 digits. So same basic idea for the 2-digit number. We have 8 different possibilities for our 10s digit, 9 for the 1s digit. 8 times 9 is 72. And then we just have, well, we just have 8 versions here, right? So now we add 648, 72, and 8 all together. And guess what we get? We get 728. Oh, yeah. All right, we should probably put the answer on the blank or else it doesn't count, right? Okay. Next question. In a particular word game, there are 2 types of letters. Shocking. Vowels and consonants. Vowels are worth 1 point, consonants are worth 2, and a Y is always a consonant. When more than 1 letter of the same type appears consecutively, each word is worth twice as much as the letter before. For example, cup is worth 2 plus 1 plus 2, 5 points. Whereas sly is even better because all of them are consonants. So we have 2, and then twice of 2 is 4, twice of 4 is 8. So that's a total of 14 points. What is the absolute difference? Now this word absolute means absolute value. So we have to have a positive answer here. Difference between the value of queuing and, is that even a word? I don't know. I teach math. All right, so here we go. So Q is a consonant, so that's worth 2 points. We have a U, which is a vowel, that's worth 1. We have another vowel, so we're doubling 1 to make 2. We have a third vowel, 2 times 2 is 4. We have another vowel, so 4 times 2 is 8, followed by another vowel, which is 8 times 2, which is 16. And then we have a consonant of N, which is 2, and then a second consonant, we double that for 4. So when we add these 3 numbers together, we get a grand total of, what is our grand total? 39. All right, quick maths. Now, this, we have only consonants here because of the silly rule saying Y is always considered a consonant. So, here we go. I feel like we're going to get a big score on this one. So S is worth 2, Y is worth 4. I'm going to just write it over here, so I'm going to use space pretty quick. So then 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. 32 times 2 is 64. So when I add all of these together, I will get 126. So we're looking for the absolute difference between the two. So we're just subtracting these two numbers. 126 minus 39 gets us 87. So we will have 87 points between the two. All right. So number 9. All right, so I'm going to scroll this up a bit. Using each digit 1 through 6 inclusively, which simply means we're using all of the numbers, exactly once, how many 6-digit integers can be formed that are divisible by 6? All right, well, let's figure out how many different numbers can we come up with if we're having a 6-digit number with 1 through 6, and we can only use each number once. So 1, 2, 3, 4, 5, 6. Now we have to have each of these numbers. We only have 6 numbers, so we have 6 different options for each of these places. Right? No, that's not true. That means we're doubling it. What am I thinking? So if I use a number here, then I only have 5 different options for my second blank. 4 options, 3 options, 2 options, and 1. So 6 times 5 times 4 times 3 times 2 times 1. Well, that's just 6 factorial, which is equal to 720. So we know we have 720 total options, but not all of them are going to be divisible by 6. So let's talk about divisibility rules really quickly. So we know that for a number to be divisible by 6, it has to be divisible by both 2 and 3. And for a number to be divisible by 2, it has to end with an even number. Well, we have half of these possibilities are even numbers. So that means only half of these possible values can be divisible by 2. So right now we're at 360. Let's check on the 3. So for a number to be divisible by 3, the sum of all the digits has to be a number that is also divisible by 3. So 6 plus 5 plus 4 plus 3 plus 2 plus 1, as luck would have it, is equal to 21. And 21 is divisible by 3. So all of the combinations that we've come up with will be divisible by 3. Only half of them are divisible by 2. So that means we have a total of 360 digits that are divisible by 6. All right, greatest problem, here we go. So points D, E, F lie on the perimeter of ABC, triangle ABC, such that AD, line segment AD, BE, and CF intersect at point G. If AF is equal to 3, BF, BD, and CD are 2, and AE is 5, what is the ratio of BG over GE? So here's how to think about this. This is more of like a physics problem than anything else. Think about everything as a seesaw, right? And so on a seesaw, I have my fulcrum. And so let's say I have a 10-pound weight that's placed 5 feet from the fulcrum. And I want this balance, I want this seesaw to be balanced, and I only have, let's say, a 25-pound weight. So to keep the seesaw balanced, I would have to put my 25-pound weight 2 feet away from the fulcrum, because 10 times 5 is equal to 25 times 2. I have to keep that balance. So with that in mind, if I think of point F as the fulcrum and the line segment AB as a seesaw, if this length is 3, AF is 3, and FB is 2, that means the weight that I would have to put on B to keep this balanced would have to be a 3-pound weight, and then that would mean a 2-pound weight would have to go on A. And that would keep line segment AB balanced. Well, using the same logic, point D is in the at the midpoint of BC, so that means to keep this line segment BC balanced, we would have to have a 3-pound weight on point C as well. All right, well, if I have a 2-pound weight on point A and a 3-pound weight on point C, how much weight is being exerted at this fulcrum point right here at E? Well, that weight is going to be the sum of the two, the weights at the 2 points. So I have a total of 5 pounds of weight that are being placed on point E. And just for the record, that means there's also 5 pounds at point F and 5 pounds at point, or sorry, not 5, 6 pounds at point D. All right, so now we know that there's a 5-pound weight at E and a 3-pound weight at B. Well, remember, we are multiplying the lever arm from the force, or by the force that's being exerted at that point. So for G to be our fulcrum and line segment E and B, or EB, to be balanced, that means this lever arm right here, that would be BG, so line segment BG would have to have a length of 5, and GE would have to have a length of 3, so that we remain balanced. Therefore, if we're trying to find the ratio of BG over EG, well, the length of BG is 5, the length of GE or EG is 3, and so that's already in simplest form, so voila, we have our answer. Woohoo. So really cool, graceful problem in number 10, and then we had some not so challenging problems for the rest. So I hope that was helpful. If you have any questions, please let me know in class. I'd be happy to answer them.